Your phone can track your face in real time, and the math behind it is surprisingly simple to understand. So here is the problem we are trying to solve. Imagine you have two frames from a video taken just milliseconds apart. You want to know how each pixel moved between those two frames. That movement is called optical flow, and figuring it out is how cameras track faces, how self-driving cars detect obstacles, and how video stabilization works. The naive approach most people think of first is just comparing pixels one by one. You look at a pixel in frame 1, then search the entire second frame to find where it ended up. Simple enough, right? But here is the problem. A single pixel gives you almost no information. If a pixel is just one shade of gray, it could have moved anywhere and you would never know. This is called the aperture problem, and it basically means one pixel alone is useless for tracking. So what does the Lucas-Kanade method actually do differently? Instead of looking at one pixel, it looks at a whole small window of pixels around the point you care about. It assumes all the pixels inside that window moved by roughly the same amount. Now you have a whole neighborhood of information to work with, instead of just one dot. Then, it sets up a system of equations, one equation per pixel in the window, and uses a technique called least squares to find the best possible answer for how fast and in which direction that patch of image moved. The clever part is weighting pixels closer to the center more heavily, so the edges of your window matter less than the core. The result is a robust, noise-resistant way to estimate motion that powers some of the most important computer vision systems in the world today.